Good afternoon and welcome. I'm joining you today from the land of the Ngunnawal people, who are the traditional owners of the Canberra region. The Academy acknowledges and pays respect to the traditional owners and the elders past and present of all the lands on which we operate, live and work. They hold the memories, tradition, cultures and hopes of Aboriginal and Torres Strait Islander peoples of Australia. My name is Anna Maria Arabia and I'm the Chief Executive of the Australian Academy of Science. I'm thrilled to be here today for a special event as part of our annual Science at the Shine Dome. Traditionally, Science at the Shine Dome is a 3-day event in May where Australia's most influential scientists gather at the Shine Dome in Canberra. This year, however, as we all know, things look a little different. But in some ways, it's even better because we're enabling participation across Australia and across the world. So wherever you might be joining us from, we welcome you sincerely. We launched Science at the Shine Dome back in May with the Academy's inaugural Ruby Payne-Scott Lecture. And since then, we have also celebrated the Matthew Flinders Medal and delved into science and the public good during our symposium. If you missed any of these events, you can watch the recordings on the Academy of Science website where they're published 1 month after the event. This afternoon, we're here to celebrate 5 of the Academy's awardees, the recipients of some of the Academy's career awards. We're delighted to be able to celebrate these awardees and we look forward to hearing from them soon. Before we get started, I would like to acknowledge our event partners, 11 of which have made this 2021 event series possible. All of our partners are displayed on the screen and I wish to make special mention of Unibank, the Department of Industry, Science, Energy and Resources and Evans and Partners. These partners continue to support the Academy and we greatly appreciate their ongoing support. The contribution of our partners, big or small, enables the Academy to continue to remain independent, foster and champion excellence, and make science available to everyone. So thank you. We will now start the presentations by our awardees. If you have a question for them, please enter it into the Q&A section on the right-hand side of the portal. Now, to introduce our first awardee, please welcome Academy Fellow and Council Member, Professor Louise Ryan.
Thank you, Anna Maria. I too am delighted to be here today, celebrating Academy awardees. In particular, I join you today to celebrate the 2019 Hannan Medal. The Hannan Medal is a career award that recognises outstanding research in any of the fields of statistical science, pure mathematics, applied mathematics and computational mathematics. It honours the contribution to time series analysis of the late Professor E.J. Hannan, Professor of Statistics at the Research School of Social Sciences of the Australian National University. I'm sure many people, like me, remember Professor Hannan with great fondness. So in 2019, this medal was awarded to my dear colleague, Professor Alan Welsh. So before we hear from Alan, I'd like to read the official citation. Professor Welsh has developed useful new methodology, derived the properties of these and other methods, and clarified relationships between different statistical methods, all in a particularly wide variety of problems. He has developed innovative new models for count data with many zeros and compositional data, including for longitudinal and clustered forms of these data. He's made important contributions to inference, robustness, the bootstrap, and model selection for mixed models. His research on applications of smoothing methods to clustered data demonstrated that remarkable improvements can be achieved by taking proper and careful account of the dependent structure when constructing a smoother. Professor Welsh contributed to resolving how to do maximum likelihood estimation for sample survey data, and in ecological survey analysis, he made especially important contributions to distance sampling and occupancy modelling. All of this work and more has a characteristic of theoretical depth combined with substantial practical relevance. Congratulations, Alan, and now to Alan's presentation.
I am honoured to be awarded the Hannan Medal, named after the very distinguished statistician Ted Hannan. I am currently the E.J. Hannan Professor of Statistics at ANU, so the medal adds another very nice connection between me and Ted. Ted was a formidable figure. I recall more frequently as I get older, Ted in his late 60s, commenting that he was slowing down mentally and finding it much harder to learn new mathematics. Ted, who was mathematically very powerful, was then still learning new material much faster than many younger people. Ted came into my office one morning to ask my advice on a problem he was working on. After covering the blackboard with detailed mathematics, he announced that I had been very helpful and left. Now, any insights Ted might have gained came entirely from himself. This is not unusual. The effort of explaining a problem to someone else often gives one ideas on how to approach it. But I was pleased with the thought that I might have helped Ted, even if only by listening to him. Inspired by Chip Heathcote and Peter Hall, my early research focused on robust and non-parametric methods. I was interested in methods involving order statistics and the extent to which these could be extended to regression problems. I also became interested in non-parametric smoothing. A series of papers with, at different times, Andreas Ruckstuhl, Ray Carroll, Jihong Lin, and Naixin Wang produced unexpected results about how to incorporate cluster structure into kernel and spline smoothing. Statistical ecology has been a very good source of interesting research problems for me. For example, observing a high proportion of zeros is a common problem in modeling count data. I met this problem in the context of modeling possum counts with Ross Cunningham, David Lindenmayer, and Christine Donnelly. I developed the methodology further for a survey of seabird nesting on Northeast Herald Island. An interesting finding was that the simple transformation-based methods that were then being used to analyze the data are unreliable. I went on to develop generalized additive models for extra zero data with Simon Barry, and a very general heteroscedastic nonlinear model for extra zero data with Andrew Joe. My PhD student, Melissa Dobby, and I developed a marginal model for longitudinal data. And more recently, Eva Cantoni, Joanna Mills-Fleming, and I implemented a mixed model for clustered data with extra zeros to explore trends in the hammerhead shark population from fish bycatch data. Ecological surveys are complicated by measurement errors arising from the non-detection of plants and/or animals that are present but unobserved. Simon Barry and I showed that distance sampling, a method that tries to adjust for non-detection in population size estimation, made unacknowledged assumptions. My PhD student, Gavin Melville, and I proposed a calibration approach to avoid making uncheckable assumptions. Occupancy modeling provides a different way of handling non-detection through repeated surveys. In work published with David Lindenmayer and Christine Donnelly, I showed that the method works well when the assumptions hold, but can be very misleading when abundance varies over sites and detection depends on abundance. A fundamental question in the model-based analysis of standard surveys is how to do maximum likelihood inference. The elegant answer, developed and explored with a number of colleagues, including Ray Chambers, Alan Dorfman, David Steele, and Sujin Wang, is to use the missing information principle that is the basis for the EM algorithm. Magnitude-based inference is a method that became popular in sports science because it seemed to be better able than standard methods to find small effects in small samples. Emma Knight and I showed that this was achieved by an under-the-counter increase in the type 1 error, so is not a valid method for statistical inference. I started working on a bootstrap prediction method for robust model selection in regression and generalized linear models with Samuel Muller. This work led to the concept of model selection curves to provide a graphical representation of model stability. More recently, with Francis Huey, we've developed new lasso methods and established their properties for selecting complex generalized linear mixed models. I've also collaborated with Paul Kabila and his students on the exact properties of frequentist model averaging. This work explores the issue of how well model averaging succeeds in constructing post-model selection inference, arguably the most important unsolved problem in statistical inference today. My PhD student, Janice Seeley, and I developed new methods for analyzing compositional data, that is, vectors of the proportions of the ingredients in mixtures. Motivated by the need to develop flexibility in the handling of zero components, which pose difficulties for the standard log ratio approach, we mapped the data onto the positive orthant of a hypersphere, and then treated the data as spherical. We also developed a mixed model that is useful for analyzing compositional survey data, and a general method for dimension reduction. Mixed models have been an important theme in my research, appearing in many of the topics I have mentioned. For nested models, my PhD student Alice Richardson and I obtained useful asymptotic results for maximum likelihood and REML estimators. We then developed robust estimators for these models. This is a difficult problem due to the lack of a group invariance structure in the models. Recently, in a different framework, my PhD student Ziyang Liu and I developed asymptotic results that greatly simplify inference when the clusters are large. A series of papers with at different times Chris Field, Peng Chen, Mayuk Samantha, and PhD student Pauline O'Shaughnessy showed that in very small samples, non-parametric bootstrap distributions of the variance parameters underestimate variability, and we proposed new methods to improve on them. Wanjun Yoon and I studied the effect of ignoring dependence in the covariates in a linear mixed model. We found that the usually concave likelihood and REML criteria can become multimodal, changing the properties of the estimators. In my research, I have found great value in exploring simple special cases computationally and theoretically. It still fascinates me that asymptotic results that strictly apply at the unattainable end of a sequence actually provide insights and practically useful approximations that work early in the sequence. Computational skills have become increasingly important in statistical research. A more surprising change is that we've moved from working alone or with one other collaborator to working in larger teams. In looking back over research, it is easy to make it look as if everything followed a logical sequence in which we knew what we were doing and simply did it. In fact, I've spent most of my time exploring and trying to work out what to do. Formulating the question is already partly answering it. I often did not know where I was going. I made choices from curiosity or interest, and with luck, some turned out well. We all need support and good luck in our careers, and I appreciate that I've had plenty of both. There are many people to thank. My family for their infinite patience and support, my teachers, mentors, colleagues, collaborators, friends, postdocs, and students. Thank you all.
Thank you ever so much, Professor Welsh, for that fascinating presentation. It's now my absolute pleasure to welcome you live with us.
Thank you very much. I'm very pleased and proud to be here.
It's deeply deserved. Thank you. Your presentation was absolutely fascinating. We have some time now for a few questions. I might get things moving, but if members of the audience wish to ask a question to Professor Welsh, please do put them into the Q&A section of your platform on the right-hand side of your screen, and we'd be happy to transmit those to Professor Welsh. I'll start from the beginning. You mentioned, you gave us some insight into what it was like to work with Ted Hannan and how inspiring that was. And a lovely example of you walking into his office saying that you'd helped him with a problem he was working on, if doing nothing more than letting him verbalise what he was saying. Tell us a bit more about that relationship and how much of a mentor he was for you, and if there are other ways that Ted's work influenced yours in a very foundational way.
Certainly, thank you. Ted was, a good example is that Ted was very fond of quoting the famous quote from Einstein that everyone should have a cobbler's job. And in our context, Ted viewed teaching as being that job that gives us something more practical to do than research, that supports our research and ensures that we are immediately useful. And I've always kept that in mind. I've greatly enjoyed teaching, and I've found it benefits from the research and in turn benefits doing research. So that came very directly from Ted.
Thank you. You touched on some examples of applying your statistical methods in ecology. That would have necessitated some initial collaborations between those in the ecological field. Firstly, how did they come about? Then I'd like to ask you as a next question around some of the assumptions and how you worked with those. But how did some of those areas that you ended up collaborating with to apply your mathematics come about?
Well, I was very lucky as a young statistician at ANU. At that time, the Statistical Consulting Unit had just been created, and Ross Cunningham, who was an outstanding applied statistician, was working in the consulting unit. And from time to time, he would ask me for advice on problems and share problems with me. And David Lindenmayer was a young student who Ross introduced me to, and that is how I started working with David. Also through Ross, I met other researchers, mainly at ANU. As my career went on and I got to know more people around the world, for example, Eva and Joanna, who brought in the hammerhead shark data, they introduced me to ecologists that they knew, and so my collaboration expanded.
It's fantastic, and something we need to bear in mind in the context of the pandemic in terms of being more deliberate in the way we expose our young researchers to those opportunities, particularly whilst they can't travel and kind of run into people either on campus or at international conferences. Yes. I have another question that goes to, can you give us a little bit more appreciation or further your thinking on why is it so challenging to reduce the assumptions and improve accuracy? You spoke a little bit about those challenges in your presentation. How do you approach that?
I did. So in all statistical analysis, there are always some assumptions. But some assumptions can be at least partly checked by looking at the data. And those are obviously preferable to assumptions that really can't be checked from the data. So always in trying to improve methods and understand them, we would like to reduce the assumptions as much as possible and then go further and reduce them to assumptions that can be examined and at least partly confirmed. You can't get away from the assumptions completely. And in some very difficult problems, for example, involving missing data, so that your problem is in a sense incomplete, you're then forced to rely on some assumptions that can't be checked. But a general theme and a general approach, which I like, is to try to reduce those uncheckable assumptions as much as possible.
Thank you. We have a question from the audience. It said, you mentioned, it's from Professor Malcolm Sandbridge, you mentioned good fortune in your research. Can you tell us what role serendipity played in your research achievements?
Well, thank you, Malcolm. I think it's very difficult to point to research that isn't affected by serendipity. There's, first of all, finding the problems, and as I indicated, with making contact with ecology, I was in a good place at a good time, and that worked out well for me. But working on problems, choosing which directions to follow, is one aspect. But then the second aspect is whether your colleagues think you've made good choices or not. And this can be really down to good luck. When I was in my first appointment at the University of Chicago, Rudy Baran came to give a seminar, and he was a very distinguished theoretician at the time. And I remember him saying to me that one should follow one's own interests, and maybe you'll be lucky and things will work out for you. And in retrospect, I'm very happy that that's happened, but there's very little you can do to bring it about. This is why I'm very explicit about saying to young colleagues that you do need a certain amount of luck, and there's not much you can do about it.
Mm-hmm. I think that's an important lesson and principle to try and remain creative and follow your instincts, and also create the space for that mental creativity in a increasingly time-poor world. I imagine that's one of the challenges that many researchers face. I have another question here. Do you know how your methods have helped measure and manage the sustainability of the animals you worked on? I think it's fair to say that when most people think of ecology and sustainability in that area, they're probably not thinking of the mathematics behind it, but it's so crucial. Draw that link for us, please.
Yes. Let me first of all acknowledge that, of course, I'm not an ecologist, and what I've learned largely comes from working with people who are ecologists. And the way we tend to collaborate is that they tend to write the papers which, if you like, focus more on the policy and predictive aspects of what might happen into the future. As you well know, David Lindenmayer is very, very good at that. From my side, what's important is being in close collaboration with people like David, who have a very good feel for what the important questions in their field are. You can't come in from the outside and just start doing things and think people will be interested or will care. It's very important that you link up with excellent other scientists and work with them. So for another good piece of advice for young statisticians, this came from Chris Field, was to identify excellent scientists and, if you can, work with them.
And the essence of collaboration, it's a true partnership. Thank you. If you had to choose, Alan, one of the methods that you've improved or developed, which is the one you'd be most proud of? And equally, which is the work you've not yet cracked that you're really determined, or the one that keeps you up at night to determined to break through some of those barriers?
Those are very difficult questions to answer. I think that in terms of insight and understanding, there are a range of methods which have made really good contributions too. Some of those, as I indicated at the end, are ongoing contributions in linear mixed models, which are very widely used and very, very important. I find that there's no shortage of new problems, and very challenging problems. But I would say that as I keep on going, they keep me up less at night, not because they're getting easier. In fact, they get harder as you keep on going, which is an interesting and unexpected phenomenon, but more perhaps because of the consequences that in working with other people far more, the burden tends to be shared. And so when you're stuck, you're all stuck and you're all working very hard together. And I think this is one reason why research in statistics has changed from a very isolated pursuit to far more of a team activity.
Indeed. You spoke in your presentation about different ways the work you do is changing. How have computational skills impacted statistical work, and are there some exciting opportunities of where you anticipate this will take you?
Definitely. So I think when I started, nearly all statistical research was done by pencil and paper work, essentially mathematical work. But now I find it impossible to imagine doing research without using the computer at the same time. So that's not only to do simulations, but it also is to plot things, explore things, try and get understanding from doing computation. This we use now to choose problems to look at, to confirm that solutions we think might work actually work, and then in the end to explain what we're doing and demonstrate it to others. So it's to me now inconceivable that you could work in theoretical statistics without also being good at computation. As computation changes in areas like machine learning and big data, of course, that flows into statistics too. And that creates lots of exciting opportunities, which is, I think, what you're referring to, Anna Maria.
Yes, it is, absolutely. The opportunities become limitless at some point, don't they? And it's about, again, focusing on those where your interest lies and where you feel that you're able to make a contribution. Go on.
Yes, and I was going to say that's exactly the kind of difficult choice you have to make, where you need some luck, but afterwards you find you made a good choice.
So we've spoken a little bit about collaborating in smaller groups. The work with David Lindemeyer is an example. But there's also a different paradigm or sense in working in larger groups. Sometimes it can be harder to follow a single agenda in a meeting, let alone when you're working on complex problems. What are the challenges and opportunities in collaborating, particularly with larger groups of people where there's lots of moving parts and you're trying to keep focused on a shared problem?
Sure, that's a good question. Our groups aren't that large yet. We would regard, 4 to 6 people as a large group compared to what we had before. But you're right, there are some challenges which come up as the groups get bigger. For really successful and enjoyable collaboration, you need a very high degree of trust. I mean, you're exposing your ideas with all their flaws, and many of the things you put forward may turn out to be wrong, and you run the risk of your collaborators realizing that perhaps you're not as smart or as clever as people thought you were. So one of the difficult things is making sure you all trust everybody and that the collaboration is really moving in the right direction. The other challenges are keeping everybody involved. Once a group gets quite large, there are times when it sort of breaks down into a subset of the group working on something specific, and people can easily be left out of the collaboration. This is very important when you've got postdocs and students as part of the collaboration, because you can never lose sight of the fact that you're trying to bring them along, develop their research, and help them build a career as part of what you're doing. It's not just the research outcome that's important.
Thank you. So unless there are no other questions from the audience, I have one last question for you. If you could say one thing to encourage a young person to consider a career in statistics, what would it be?
It would be that the range of problems is absolutely fantastic. The capacity to do theoretical and applied work in the discipline and to meet and interact with lots of interesting scientists is absolutely unparalleled.
Fantastic. Thank you ever so much. And again, our warmest congratulations, Alan, on this award. It's so thoroughly deserved. Thank you.
Thank you.
Now to introduce our next awardee, please welcome Academy Vice President, Professor Malcolm Sambridge.
Thank you, Anna Maria. I too am delighted to be here today celebrating Academy awardees. In particular, I join you today to celebrate the 2020 David Craig Medal. The David Craig Medal is a career award made in honour of the outstanding contribution to chemical research of the late Emeritus Professor David Craig. Its purpose is to recognise contributions of a high order to any branch of chemistry by active researchers. And in 2020, this medal was awarded to Dr. Graeme Moad. Before we hear from Graeme, I will read his official citation. Dr. Graeme Moad is recognised as a world leader in the field of polymer chemistry. His achievements range from fundamental chemistry in the areas of polymer design and synthesis and polymerization kinetics and mechanism to new materials for industrial uses, nanotechnology, organic electronics and bioapplications. His research has contributed substantially to the development of new synthetic methods for the controlled synthesis of polymers with defined architecture and composition that have revolutionized the field and resulted in highly cited publications and patent applications. Congratulations, Graeme. And now to Graeme's presentation.
Thank you for the opportunity to present on work that we have done recently, and I guess is hopefully responsible for my being awarded the Craig Medal. The talk is about a use of what we call reversible deactivation radical polymerization, and this process is basically now responsible for most of the literature in the area of radical polymerization. You can see on this slide here, which indicates publications per year on forms of radical polymerization, that in about 1995 or 1998, the publications on radical polymerization escalated rapidly. And this is basically totally due to the invention of these techniques for reversible deactivation radical polymerization, of which raft polymerization, which I'm primarily going to talk about, is one. It's of interest that even though this process these processes were invented 20 years ago, we published a review this year, which immediately became a hot paper within about 2 months, and has so far got rated 90 citations since December 2020. Raft polymerization, which, as I said, is what I'm primarily going to talk about, has also achieved a lot of status in the literature. Cumulative publications now account for of the order of 11,000 papers over the period since it was invented, and basically it continues to escalate rapidly. We recently wrote a sort of perspective of raft, which we entitled Raft Coming of Age. As indicated, this was announced to the world about 21 years ago, and basically arose out of a desire to achieve perfection in polymer structure, or at least define and limit the imperfections in those structures, and to invent what we might call living radical polymerization. However, living radical polymerization, in terms of the definition of that term, which cannot be because that says no imperfections, but we can, as I sort of point out, we can limit them at least. But what's raft and what's radical polymerization? In radical polymerization, long chains are formed, initiation occurs so as to form an active species, and then chains basically grow, adding one monomer at a time until sometime they meet and self-destruct. As a result, the product of a radical polymerization is a large number of chains which are not particularly uniform in molecular weight and not necessarily particularly uniform in composition if there are more than one type of monomer unit. In raft polymerization, we basically change that by adding a chain transfer agent, or a raft agent as we like to call it. Chains are still initiated and terminated in the same way as in conventional radical polymerization, but the activity is such that as soon as one monomer has been added, the most likely reaction is it will react with the raft agent, which basically stops one chain and starts another chain growing. And as a consequence, all chains grow simultaneously, and all chains are essentially identical, apart from a few that have the initiator and terminating groups. And in normal circumstances, these might be 1% or 0.1% of the total polymer, so they're very small. And we can do things to get around that. One of the things we've been working on very recently, over the last 2 or 3 years, is electrochemically initiated raft polymerization, which we've dubbed eRaft. We published a number of papers on this. Our first paper in 2019 talked about the electrochemical behavior of raft agents. We then studied the initiation process in emulsion polymerization. Here, raft has actually been used to generate radicals rather than react with the raft agent itself. And we can basically form radicals which then initiate and form polymers inside nano-sized, about 100 nanometers diameter, latex particles. The nifty thing about this is that under normal circumstances, only one radical will be existent in a particular latex particle, which means obviously they can't self-destruct by termination. Well, it's much less likely anyway. We published several further papers on this, looking at various ways of controlling the process. And the most recent paper was published about 2 weeks ago in Angewandte Chemie. It basically looks into the mechanism whereby raft agents react directly with electrons and shows the efficiency of this process. This work was a collaboration with Michel Coutu, who did theoretical calculations, and Stefan de Neefele, who basically used negative ion mass spectrometry to basically do this chemistry inside a mass spectrometer and show what happened and how selective it was. Another area which I've already alluded to briefly is raft emulsion polymerization and polymerization-induced self-assembly, sometimes known as raft PISA. Again, this work started a couple of years ago, and one of the early experiments we did in 2019 or so was basically to do this chemistry in a robotic platform. This enables us to do multitude of polymerizations simultaneously, so we can actually find the correct conditions for doing it and how to achieve the lowest molar mass dispersity and the narrowest particle size distribution. Basically, we do 64 experiments simultaneously, and with high throughput analysis and characterization, we can rapidly get to the right conditions for polymerization. I should say this is one of the first examples of applying this. Then we use what's called the nanoreactor concept, or which we call the nanoreactor concept, for making multi-block copolymers. This means we just add monomers sequentially one at a time. Because all the chains are identical, when you add monomers, they basically form block copolymers. And in the emulsion system, they form nanostructured multi-layered particles, remarkably specifically. This paper turned out on the cover of Macro Letters. And I should say this work was basically done at University of New South Wales by Glenn Clothier and Thiago Guimarães, Mathai and basically supervised by Per Zetterlund. One of the things you realise quickly when you're working on this is that collaboration is essential. And we published since that time, a couple of years ago, and now something like 9 papers on this, with the most recent paper on the synthesis of multi-compositional onion-like nanoparticles appearing in Angewandte Chemie last week. Well, it's an accepted article. Another thing we've been working on is what we call raft single-unit monomer insertion, where basically we insert monomers one at a time so that the whole polymer goes to a single unit chain, then a double unit chain, then a 3-unit chain, etc. So as to construct potentially sequence-defined polymers. And also we've been looking at high throughput raft polymerization, which I've already made mention of in the emulsion polymerization section, and raft in continuous flow, where we basically flow monomers through a tube to do the polymerization. And this has major advances in terms of scale-up. So in terms of the single-unit monomer insertion work, that's described in a paper that we published in Maclelland Rapid Communications. I can point out this also is a collaboration with a Chinese PhD student, another student who came to us for a short internship under the Academy America's Australia relationship and various other people from University of New South Wales. I don't have time to go into details on that, but the high throughput work that we're doing is basically where we take tubular reactors, which is what these circular things here are, and we have wavelength selective initiation, such that we can basically selectively either polymerize the monomers in a chain or activate side groups to convert monomers that way. And so we can use the same reactor setup and perhaps monomer mixture to make either branch polymers or hyperbranch polymers and get a range of diverse products. When I say we get diverse products, I mean we can choose which one we get, not we get them all simultaneously. And again, so it's a way of controlling the sequence distribution, molar mass, and other parameters of the polymer simultaneously in a high throughput way, which is potentially scalable. The last two areas I'll go over quickly, but also areas of active current research. One is that of topographical active polymers. These are polymers that have bioactivity or other properties purely as a result of their surface characteristics. Thus, we've made permanent, self-cleaning, anti-fouling, antimicrobial, biocidal surfaces by adding an additive to a polymerization during cure, or curing to cure the polymerization. This is an exercise in biomimicry, because what we're doing is creating the same sort of surfaces as are on, say, lotus leaves, for example, which give them super hydrophobic properties and things. And we discovered certain siloxane additives. In this particular case, they weren't made by raft polymerization. They're basically additives that are commercially available to provide anti-scratch properties to polymeric surfaces. But we added these additives to a coating formulation used for high-speed steel coil coating, and achieved a surface which was self-cleaning, which survived 6 months weathering out in Singapore, and a nice white surface was still a nice white surface and still retained its original properties. Amazingly, we also found these surfaces were antimicrobial. They basically killed multiple strains of bacteria. Moreover, the bacteria didn't stick to the surface, which is all very good. We're now looking at basically designing these additives for better properties and possibly even to treat to basically so we can make, I guess, coatings. And this has also been inspired, I guess, by the recent work on COVID and such things. Anyway, don't have time to talk about it more. The other thing we're focusing on is whole by strategies for plastic and circular economies. This again is an area of much current concern and the subject of several CSR emissions. The polymers I've been talking about so far are not really packaging polymers, or they're basically polymers intended for other purposes. But one of the drives of doing raft initially was basically greener polymers. The companies we were working with at the time wanted to make low VOC coatings and things. We've recently been looking into basically processes for polymer recycling. I mean, good processes are mechanical recycling, whereby you take a polymer, reprocess it, and use it for its same application. Unfortunately, that is not always possible. In fact, it's usually not possible because polymers are horrible mixtures of a multitude of different materials and contain various additives and things which prevent this. There are sort of okay but less good processes whereby we transform the polymer back to its monomer and then repolymerize it again. But again, that has quite a few limitations. A much better process that people have been dwelling on is that of taking the polymer, using biodegradation processes either to convert it to carbon dioxide or petroleum feedstock, and then basically using the normal processes to either take that to monomer, or you can even do biosynthesis to either form monomer directly or via the petroleum feedstock route. But this also has problems in that most of the polymers you encounter are, of course, not biodegradable. And you can create plans to make more biodegradable polymers, but polymers don't always have the properties you want to achieve. It's also becoming more and more possible to basically replace those biotransformation routes with industrial processes. Certainly incineration of polymers is not normally sensible. In fact, we don't want to encourage people to go around burning polymers because it's a very bad thing. But the highly efficient high-temperature incinerators with energy recovery can efficiently convert polymers to carbon dioxide. And moreover, they can take a mixture of polymers. We're now seeing processes for electrocatalytic reduction to convert carbon dioxide either directly to monomers or petroleum feedstock, with efficiencies approaching, at least on a laboratory scale, up to 70%. And this is basically getting very competitive with other routes, particularly with such things as direct carbon dioxide extraction and things. So these are other areas that we are currently working in. And that's really the end of my talk.
Now it's my pleasure to welcome live with us today Dr. Graeme Moad. Welcome, Graeme. Thank you for joining us, Graeme, and congratulations on this award. Thank you very much. The presentation was deeply stimulating, and it's very clear why you're a recipient of this award. The depth of the science is extraordinary. Graeme, we have some questions for you to the audience. If you would like to ask any questions of Graeme, please do pop them into the Q&A on your screen, on the right-hand side of your screen, and I'll be able to ask those for you. To get things going, I'll begin by asking, noting really the value of your work is so clear. How are you seeing your research taken further by others in the field?
In terms of raft polymerization, which is what I tend to focus on, raft polymerization has been taken forwards in a number of areas to commercial products. The number of commercial products is small, but it's growing, and until I guess about 2 years ago, it was very much protected by patents and things like this, which inhibit some companies and encourages others, I guess. But that we hope that the uptake will now increase dramatically, although we'd much rather it happened previously.
The work you've undertaken clearly gives a lot more control to polymer chemistry. What's been the most surprising result that you've achieved, or the most surprising aspect of your work?
I think the most surprising thing was, I guess, in terms of the initial discovery, was how you could take a process which was intrinsically chaotic. People thought that radical polymerization is a mature field suitable for making polymers, but not capable of making defined structures. And with a simple addition of a reagent, basically, and intrinsically similar reaction conditions, you could now make precisely defined structures, which and I think that was surprising at the beginning. I mean, I think there's discoveries are happening all the time. I mean, even the very recent work, the finding that we could make polymers that segregated surfaces to create surfaces which had properties we really didn't expect. I mean, I think these discoveries are happening throughout what one does.
Thank you. Graeme, can you give us some examples of where raft polymerization has been applied in manufacturing?
Yes. One example is, for example, it's been used, for example, to make pigment dispersants for paints, like house paints. So we're making, in this case, structured polymers, which basically to encapsulate pigments to as an additive in paints, and we also can do polymerization, like the emulsion polymerization, without adding surfactants as additional additives. So basically, we're making much cleaner paints, which don't have the usual additive in them, which can be a problem later on. The major applications, however, are probably not in the commodity type polymers. They're more in various specialty applications like materials for sort of drug delivery and the like in therapeutics and such things.
It's absolutely fascinating. Thank you. I mean, there's such a direct connection between our day-to-day lives through paint and through therapeutics. And certainly I'm aware of some of the research undertaken by other fellows of the Academy of Science that include some of those areas. It's absolutely fascinating. You mentioned how important and how essential actually collaboration is in your research. How have collaborations over your career played a role?
Well, I guess draft polymerization initially eventually came to be through a collaboration we had at the time with an industrial company, like in this case DuPont in the US, who basically saw what we were doing and realized that its, I guess, potential. At that time, draft polymerization hadn't been invented. And so collaboration basically provided us with the ability to continue that research, and possibly also that particular collaboration also might have also inhibited sort of research to some extent as well. Fortunately, at the time Raft was invented, DuPont was at a stage where they wanted to actually sell the products of research as opposed to keeping all the research for themselves, which they had done in other cases. So that was fortunate for our point of view. So we were able to publish the results of the invention immediately after having discovered it, more or less. But in terms of recent efforts in collaboration, essentially all of the areas I mentioned are the outcome of a collaboration or multiple collaborations. And in that case, it's basically allowed us to study the more fundamental aspects of these areas in greater detail than possibly one would if in CSIRO in normal circumstances. Some of these collaborations were initiated by people at universities. Some of them were initiated by us. It's sort of it's very much dependent on that. But in terms of having the key people to work on different areas, collaboration is vital.
Thank you. Absolutely essential ingredient in any research endeavour. We have a question from the audience, and that is, where do you envisage self-cleaning antimicrobial surfaces being most useful?
Well, we sort of, I should say that the work that was originally done related to coatings on steel, basically, and we think that's a possibility. Although that work didn't really progress in that area, mainly because of there were existing commercial products in that field, and our product, even though it seemed entirely successful, would have required a lot of development work to actually get it to something commercially viable. Currently, we're looking at or we're interested in surfaces like common everyday surfaces and common everyday coatings to create basically antimicrobial surfaces so that microbes, bacteria, potentially viruses, although viruses are a totally different sort of particle. We're not quite sure about activity in that case, but nonetheless, we're looking at that. And to make surfaces that sort of that basically don't support bacterial growth, and also self-cleaning. By self-cleaning, I mean you can just sort of spray water at them and everything, and they become totally clear like a leaf surface. I mean, it doesn't mean dust can't necessarily attach to it, but that's much less likely. And it's typically by mechanical means rather than anything about intrinsic nature of the surface.
Right. So that could be potentially applied to hospital surfaces, doors,
yes.
Potentially spacecraft.
Another thing we've briefly looked at is the surfaces of fabrics. So you can make sort of fabrics, perhaps like masks, that you might, that basically are self-cleaning and, well, that stuff doesn't stick to them. They're super hydrophobic, and bacteria doesn't grow on them, but well, super hydrophobic has a few problems if you're putting moist things through it. But anyway, there's a whole range of possibilities here, and we haven't really scratched the surface of where they go.
One challenge at a time. We'll deal with the washing of them after we've made them antimicrobial. It's absolutely fascinating to think about the applications going forward. I've got a couple more questions for you. If any of the audience members want to ask additional questions, please do pop them in now while we've still got Dr. Moad with us. A really fundamental one. What motivates you in your research?
Well, I think it's basically it's trying to discover new things. And I mean, I've always been interested in making molecules and creating and having ultimate control over those molecules. I mean, making a polymer in itself, people will tell you in any traditional chemistry department that polymers are sort of undefined things and that they're intrinsically unsatisfying. So I guess what's motivated me in polymer chemistry is being able to create polymers where you can precisely say what you've got. I mean, we're sort of heading to where nature got at the beginning of life, so to speak, where a polymer has a defined structure, and that's what you try to make. And that it also has a lot of implications in sort of green chemistry and all that sort of stuff, because a whole lot of the problems with polymers are due to the imperfections in them and the additives they contain.
Thank you. And one final question. Where would you like to take your research next?
Well, I think there's... I don't know that there's a specific place you want to take the research. I mean, one's drive at most times is to basically get the results you've already got done. And I found that a lot of new areas come by serendipitously rather than by actually designing to do something. This is somewhat of a frustration of perhaps the powers that be, but nonetheless. And I've been lucky in what I've been doing to have the latitude to actually follow up these things when they appear. And I think that's very important.
I hear this theme reoccurring, and indeed we heard it from our previous awardee, the need to have space to be creative, to explore, to undertake discovery research. It's so critical, and it's harder and harder to do so in the current environment where, as you say, we're increasingly pressured to do things by design rather than to explore that unknown and those serendipitous findings really leading and giving us the next steps. Graeme, it's been an absolute pleasure speaking with you today. We don't have time for any more questions, I'm afraid, but I'd like to again say thank you and congratulations on receiving this award. It's so thoroughly deserved. Thank you.
Yeah, thank you.
And now, to introduce our next awardee, please welcome Academy Fellow and Council Member Professor Elaine Sadler.
Thank you, Anna Maria. I too am delighted to be here today celebrating Academy awardees. In particular, I join you today to celebrate the 2021 Thomas Ranken Lyle Medal. The The Thomas Ranken Lyle Medal is a career award that commemorates the contribution of Sir Thomas Ranken Lyle to Australian science and industry, generally and in particular to his own fields of physics and mathematics. The purpose of the medal is to recognise outstanding achievement by a scientist in Australia for research in mathematics or physics. And in 2021, this medal is awarded to Professor David McClelland. Before we hear from David, I'm going to read his official citation. Gravitational waves were predicted by Einstein's general theory of relativity more than 100 years ago. After 40 years of sustained experimentation, on the 14th of September 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, detected the death spiral of two stellar mass black holes as the gravitational waves they emitted almost 1 billion years ago passed through two detectors in the USA. Remarkably, the wave moved the mirrors in the 4-kilometre long detectors by a fractional amount equal to 1/1000th of the width of a proton, in doing so, verifying one of the most challenging predictions of Einstein's general relativity. Professor David McClelland carried major responsibility as the lead Australian investigator in LIGO and has made major contributions to this famous detector, including work on quantum enhancement, which increased the observable volume of the universe significantly. Congratulations, David. And now to David's presentation.
Well, I'd like to start by thanking the Australian Academy for awarding me the Thomas Ranken Lyle Medal for 2021. In the same era that Lyle was doing research, seminal experiments in Australia on X-rays, a new form of electromagnetic radiation, Einstein was developing his theories of relativity in Germany. Einstein predicted the existence of gravitational waves, or waves in curvature of space-time, that they stretch and squash objects as they pass through the universe. So he made this prediction in 1915, but it took 100 years to verify. So this is what I call the waves of the century. It was on September the 14th, 2015, that the LIGO detectors in Hanford and Livingston in the United States had just finished commissioning. In fact, it was early morning in the US, 1 hour after commissioning ended, when this sound was heard across the universe. This is the characteristic chirp that's generated when two black holes of 30 solar mass collide with each other. And that signal, that gravitational wave, passed through the universe, and it passed through the Earth through the LIGO detectors, and this is the signal we recorded. It was not only heard across the universe, it was heard around the world. This is now an iconic symbol of gravitational wave detection. This binary black hole source, we've seen a number of those since then, until on August the 17th, 2017, about 4 years and 22 days ago, we observed this event. These are two neutron stars spiraling around each other, and as they're spiraling, they're generating gravitational waves in the band that LIGO can detect, until eventually they collide in a massive burst of gravitational waves. And 2 seconds after that burst of gravitational waves, a gamma ray burst was detected. 10 hours and 52 minutes after that, optical radiation was observed, and then infrared radiation. 15 hours and UV was observed. 9 days until the X-rays were seen, and then 16 days later, radio waves from this event were observed. 70 telescopes were trained on this event. It was the most observed astrophysical phenomenon ever. It started the multi-messenger astronomy using gravitational waves and electromagnetic waves. So what we've observed since 2015 is shown in this plot here. Masses, we call it, in the stellar graveyard. In purple are black holes that are discovered using electromagnetic means. Yellow, neutron stars that were discovered using electromagnetic. The blue and orange are gravitational wave detected signals. The orange are the neutron stars seen with gravitational wave detectors, and the blue, black holes. This presents some very interesting findings. For example, between 2 and 5 solar masses, you'll see there are objects there. These seem to be too light to be black holes, too heavy to be neutron stars. We wonder what they are. Then there's a mass gap around 80 solar masses that should have been there, where we don't think that stellar evolution would produce black holes of those sizes, but there are many of them. There's this 160 solar mass black hole, the biggest one we've seen to date. So these are phenomena, these objects are beginning to drive the field of gravitational wave astronomy. But let's go back to the beginning, back to 2015, because not just the signal just didn't create the beginning of gravitational wave astronomy, it was presented a pin-up, a precision measurement so far not copied. We reached an amplitude, we measured an amplitude of 2 by 10 to the minus 18 of a meter. That's an incredibly small amount. It's 1,000 times smaller than the size of a proton. We've effectively observed the separation between the centers of mass of 40 kilogram objects oscillate from 30 hertz up to 240 hertz with a peak amplitude of 2 by 10 to the minus 18 meters. The standard quantum limit of motion for an equivalent object is only 2 by 10 to the minus 19 meters, very close to putting these objects into quantum ground states. So we may be soon able to observe human-sized objects behave quantum mechanically using these gravitational wave detectors. But let's now take a look at the instruments we use to do this. This is the layout of the LIGO interferometers, and it's a fairly busy slide. I'll take you through some of the major points of it. Light from a pre-stabilized laser, 200 watts, is shone into the interferometer. It's cleaned before it enters, passes through conditioning optics. At this point here, called the main beam splitter, half the light gets sent vertically and the other half goes horizontally. The light is then stored in cavities in these arms before it returns to the main beam splitter and is compared to the light coming out of the other arms. And that light then enters through steering mirrors and is shone into our photo detection system. Now we want to set this up and have it such that in the absence of a gravitational wave, there is no light coming out of the detector. So that when a gravitational wave comes through, which squeezes and stretches the arms, a signal is produced. Now to do that, we have to make sure all the optics, everything in this device is totally isolated from everything on Earth. So it's in massive vibration isolation systems, massive vacuum systems, and so on. But we also have to make all of the elements, all of these optical elements work together. And that's called a control system. That's one of the main things that my group worked on to begin with. We developed this control system by using an auxiliary laser, using a green laser, along with the infrared laser, which is the main science laser, this red beam. We shine both a red laser and a green laser into the interferometer, and we can use the information extracted to figure out where all of the optics are and make them work together. Now, this diagram here is in the end station of one of the interferometers. You can see how big this is. This is a person standing inside the interferometer. You can see the green beam, the auxiliary laser beam we use for control systems, and the infrared beam would be bouncing along this arm here. Another contribution we've made is in these devices called steering mirrors over here. Now, these steering mirrors are small optic suspensions. There are 20 of them throughout the LIGO interferometers, and they're used to steer the path of the lasers. For example, the light that comes out of the interferometer is directed by the steering mirrors through this device called a Moad cleaner into the photo detection system. Now, these steering mirrors were designed at the ANU and built in our workshop. So it's kind of cool to know that we've got these mechanical devices sitting in these massive detectors overseas. The last thing I want to point out on this plot is the most recent contribution, and that's squeeze light injection. Now, it turns out that no matter how well we try to control the laser, its amplitude and its phase are fuzzy. This is due to quantum mechanics. At the very limits of measurement, there's a slight fuzziness in how precise a laser beam is. Now, normally this fuzziness, this quantum noise, doesn't affect us. But when you're trying to measure an amount which is 1,000 times smaller than the size of a proton, these effects can mask the signal. Now, we can't get rid of quantum noise. But what we can do is to manipulate it so that we can use something called a squeezed light state, inject that into the interferometer, and manipulate it so that the quantum noise doesn't affect the measurement. Squeeze light generators have been pioneered at ANU. We developed the first squeezing for gravitational wave detection in around 2004, and it took to around 2016 to work with the community to install these squeezers on site. And this shows some of the ANU team. But what's next? Well, NEMO. NEMO is the Neutron Star and Extreme Matter Observatory. It's a pathfinder to a future Australian third-generation detector. But that's a story for another time. I'd like to end by acknowledging the people who helped along the way. In particular, the Australian Research Council, without whose support and funding to put those components into the detectors, Australia would not have been one of the 4 partner countries in the first direct detection of gravitational waves. I'd like to thank my collaborators at UWA and University of Adelaide, who also supplied systems for the LIGO detectors related to distortions and instabilities. The LIGO scientific collaboration is a team of over 1,500 scientists from more than 15 countries around the world working on LIGO detectors. But in particular, my group at the Australian National University, without whose hard work and dedication over 20 years, I would not have received the Lyle Medal. So this is in their honour as well. Many have spent their research lives working on LIGO both in Australia and at sites in the US. It's been a great journey, and I'm pleased I was along it with you. Thank you very much.
Thank you ever so much, Professor McClelland. How absolutely fascinating. It's my absolute pleasure now to introduce you live to our audience today. Thank you and congratulations.
Thank you, Anna Maria. It's a great outcome, a great award. It's for a career's worth of effort, but just not from me, as I said before.
I have very fond memories of speaking with you when yourself and your collaborators won the Prime Minister's Prize for Science. And I think you said something similar at the time. It was very clear to be a group effort, but, we credit where credit's due. Your contribution has been nothing short of phenomenal.
Thank you.
It's such a remarkable story, and I think one that inspires and piques the imagination of many, young and old. We heard how Einstein's theory of relativity took 100 years to verify, and it took 40 years of sustained experimentation. How fortunate do you feel to be in this moment of time? You might have been doing your research some decades ago, or who knows in the future, but it's a unique period in this field.
Absolutely. Many people who began their research with the dream of being involved in gravitational wave detection, who didn't even live to see it in the end. And I was very fortunate to have come along at the time I did, at a time when the technologies made it possible. I mean, Einstein himself thought it would never be detectable, and so he put him down as a curiosity. But he didn't have lasers, he didn't have electronics, he didn't have the beautiful mirrors and so on that we had 100 years later.
And that infrastructure is so critical. I mean, the sort of kit that we saw in your slides, it's phenomenal. They are such complex pieces of infrastructure. No doubt Australia doesn't have them all. We rely on shared infrastructure to make these discoveries. How well equipped are we? It looks really comprehensive, but I'm sure there's more you could use.
Well, in terms of doing the research and the development, Australia is quite well equipped. The ANU labs, we've got a nice building funded by the ANU in the first place, with lots of equipment in it that enables that research to be done. We have a nice facility out at Gingin in Western Australia for the R&D, but that's taking that research and putting it into an instrument. That is not something we have, but it's something we dream of having one day.
Absolutely. In one of your slides called Masses in the Stellar Graveyard, it tells a story of what that first discovery has led us to. Mm-hmm. Give us more of a sense of the new discoveries that have been made since the birth of gravitational astronomy.
Well, in particular, with the binary black hole system, when we first turned the LIGO on, and back in 2015, we weren't actually expecting to see a signal, not to see a signal that was clear in the data. We thought we would have to be running algorithms through to extract the information, but this signal came through clearly observable. And it was due to an event we didn't actually think we would see. That was 30 solar mass by black hole systems. We knew that if they existed, that would produce a signal, observable signal, but it wasn't known whether they existed or not. So the turning on of our instruments
not only discovered gravitational waves, it discovered these 30 solar mass black hole systems, which are now many of the events we've seen. And it, as I said earlier, it led to this phenomenal experimental outcome of being able to make measurements of that magnitude.
So is it a case of the more you know, the more there is to know?
But we really hope so. And that's what the discovery is all about. It would be really surprising to me if the discovery of gravitational waves did not lead to understandings about the universe, objects, discoveries in the universe that we don't today know of their existence. Any new field, I mean, from the time Galileo pointed his telescope at the sky and discovered the moons of Saturn, moons of Jupiter, and so on. From the time the pulsars came through our radio telescopes, every new window has brought something brand new and led to a deeper and deeper understanding of the universe. Gravitational waves will do that.
May I ask, has the pandemic, the COVID-19 pandemic, slowed down the research effort in this area because it's so dependent on collaboration and access to infrastructure?
Well, it, again, was fortunate that it came along at a time where we'd finished the most recent observing run, and the instruments were down and we were upgrading them. A lot of the upgrading had already been determined what we needed to do. Those pieces of equipment were being manufactured in laboratories and in engineering labs and being prepared to install. So at that time, a lot of the in-the-lab work had been done for the next steps.
I see.
But the impact will be, all the time we are trying to figure out how to make these detectors better and better and better. So I think the impact of a couple of years of COVID means that those discoveries, those realizations how to improve the detector may slow down a little bit. But it also gave us time to think about, well, what we really want to build in the future.
Perhaps some of that creative space we've spoken about with other awardees today, to think about next steps, to think in a unrestricted way, perhaps. And of course, time is relative when you think of the 100 years. So if there are any questions from the audience, please pop them into the Q&A and I'd be very happy to relay those to Professor McClelland. My next question is, you alluded to some of the areas research is heading in, including being able to see human-sized objects that behave quantum mechanically. To a layperson, what does that mean exactly and why is it important?
Well, in the quantum world, there's this concept of coherence. You can create particles which are quantum linked to each other, to electrons, and you can send these electrons to different paths out into the universe. Then you make a measurement of one of them in one part of the universe, it immediately determines what the other one was doing. So this is called Einstein-Podolsky-Rosen. This is the name for it, entanglement. It's not action at a distance. It means having made a measurement of one of the linked particles, the other one is determined. But we wanted to know, is there a size scale at which those sorts of coherences disappear? Will they exist if we could sort of quantum entangle two mirrors and send them to different parts of the universe, or in the future do a Star Trek and teleport two people? So that type of understanding means are there mass scales at which quantum effects don't occur anymore? And that's what we can discover by building larger and larger objects and finding out whether there's a certain scale where, for example, gravity itself causes quantum decoherence or quantum effects to disappear. So that's the science fiction angle to it, but it's rooted in some really interesting physics that can be done.
I think you might have inspired some of the next generations of astronomers to study it. We have a question from Ron Eckers. Thank you, Ron, for being with us today. And excuse me if I get any of this wrong. The predictions of Einstein's theory are confirmed. So what is new is the 3M sun binary. Does this mean the physicists will now lose interest and it's for the astronomers to understand where this binary came from?
I think it's certainly for the astronomers to understand it, that it's for the physicists. Where do we define? I actually don't really draw the line between astronomy and physics too much, Ron, and I think it's all curiosity driven about understanding the universe. And when we look, one of your earlier questions, Anna Maria, is about what's next. Well, one of the next things we want to do is understand the nuclear physics inside a neutron star. That's when two neutron stars collide, we can learn about from the gravitational waves what's happening with the particle nuclear physics at such extreme densities. So it needs astronomers and physicists to work together to make those discoveries. And I think the great thing about gravitational waves, it drives physicists and astronomers closer together.
Don't all astronomers start as physicists?
Perhaps the other way around as well.
The other way around. Thank you. You also mentioned the Neutron Star and Extreme Matter Observatory, or NEMO. But in this case, it's NEMO that will be doing the finding. Could it help identify some of those objects you mentioned?
It's the NEMO is the one where, certainly in terms of this nuclear physics experiment in the universe, that's what it's sort of aimed at. And it's it's one of these things that came about through some time, I guess, in COVID, where the AusGrav, the ARC Centre of Excellence for Gravitational Wave Discovery, it was a collaboration amongst us to say, well, what can we do in Australia on a scale which is perhaps within a funding envelope that makes a major contribution and may lead in the future to us having a full-scale gravitational wave detector in this country. And this is the concept of NEMO, where we can build, using new technologies, an instrument focused on what's called the kilohertz gravitational wave band, where the signals that come out tell us about what's happening inside neutron stars. And then doing that, we also test the technologies for future detectors.
Fascinating. Can you give us a sense of how large and ongoing Australia's role is in the LIGO project?
AusGrav, as I mentioned, the Centre of Excellence, is about 150 to 200 people now. Most of those are in LIGO. LIGO, we make up about 10% of the LIGO scientific collaboration at the moment. I'd like to think we punch above our weight for the size that we are. We make major contributions across many of the instrument development as well as the data analysis efforts, and accompanying getting the measurement out is being able to extract the information from that measurement, and that's a huge data analysis problem. And we also have experts in data analysis and computation in AusGrav as well that are driving those fields within the global collaborative effort.
Thank you. Professor McClelland, you showed us photos of your team at the ANU and also paid tribute to your collaborators at the University of WA and the University of Adelaide. All of them part of 1,500 scientists from 15 countries, which is phenomenal collaboration. What kinds of expertise are included in the Australian group? What would be considered Australia's key contributions to those mass collaborations?
The squeezing that I mentioned earlier, this quantum noise reduction, which is Australia and ANU in particular is very globally known for that effort. In fact, the beginnings of putting these devices into the detectors overseas started in Canberra. We trained the groups from the US and Germany who went on to develop their own squeeze sources, but the centre of that, I'm proud to say, began with the ANU effort. And the ANU effort in squeezing, I mentioned we focused on gravitational waves in around 2004, but it was in 1989 when I first came to Canberra and joined Hans Barkel's group that Hans had the vision then to start the quantum optics as an area of research at Australia. And this is one of the outcomes in the long term.
The rest is history, as they say. What first inspired you?
Sorry, Anna-Maria.
Please go on.
I think I rightly announced what we've done here, but we also have the expertise in WA on what's called instabilities. These, if you turn on a laser interferometer high enough power, it drives the system to become unstable. And if UWA hadn't predicted that outcome and ways to mitigate it, then LIGO may not have reached its sensitivities it's achieving now. University of Adelaide, in terms of distortions in mirrors, they are experts in how to read out those distortions. So we can point to some real key contributions that make those detectors work.
Yeah, phenomenal contribution by Australia. What first inspired you to pursue a career in, I'll say, physics?
It was actually, I think, many people of my vintage. It was Armstrong, watching Armstrong step onto the moon. That sense of discovery, that sense of excitement. I mean, I was in high school, and the school was not very well off school. We had one black and white television, but that moment is one of the most vivid memories I have, as I think, as I said, for many people my age. And later on, with the discovery of gravitational waves, I really had some of that sense come back to me. It was almost like a world-stopping event again, where all of the troubles that are happening around the world, the detection of gravitational waves was one of those things which was a good news story in 2015, and one of the great outcomes of the work is to have brought the world a bit closer together.
Yeah, I think that's true. I wasn't born when man stepped on the moon, but certainly the gravitational waves experience was one I won't forget, and I'm sure it too has inspired many. I'll just ask the audience if you have any questions, now's the time to answer them, because I'm about to go into the final questions, or the final question actually. So what would you say to a young person considering a career such as yours now?
A young person considering a career well, it's actually very different now to when I began, and I'm just so in awe of what our young academics achieve these days, Anne-Marie. When I started teaching and research, they were the two planks. That's what you had to do. Now it's teaching, it's research, it's spinning off companies, it's developing commercial applications, and what I see them achieving, as I said, is it's fantastic. They're taking these technologies and this route from fundamental science to applied outcomes is really traces why we should be doing fundamental research. So I'd encourage them to do fundamental research. I'd possibly echo in their ears the advice I was given when, in a slightly different way from my supervisor. I said to him, look, I want to do a PhD to learn about the universe. And his response to me was, but do you want a job afterwards? You better do experimental physics.
I'd hope there's room for both these days. David, it is always such a pleasure to speak with you. Thank you for your presentation. Warmest congratulations as the recipient of this award.
Thank you very much. It's been an honour.
Thank you. And now to introduce our next awardee, please welcome back Professor Louise Ryan.
So thank you, Anna Maria. I'm delighted to be here again today. This time I join you to celebrate the 2021 Hannan Medal. So as we heard earlier today, the Hannan Medal is a career award that recognises outstanding research in any of the fields of statistical science, pure mathematics, applied mathematics, and computational mathematics. It honours the contribution to time series analysis of the late Professor E.J. Hannan, Professor of Statistics at the Research School of Social Sciences at the Australian National University. And this year, the medal was awarded to another of my colleagues, Professor Mathai Varghese. Before we hear from Mathai, I'd like to read his official citation. Professor Mathai Varghese has made highly influential contributions to the field of geometric analysis, which relates geometric, analytic, and algebraic properties of possibly infinite dimensional manifolds. Among these are his co-inventions of fractional index theory and projective index theory that have received international recognition for explaining the mystery of the analytic counterpart of the A-hat genus. His recent joint work extending the fractional index theorem to infinite dimensional loop spaces is also of immense significance. His joint body of work proves the conjecture that fundamental quantization commutes with reduction in the non-compact case. Also seminal is his joint work on twisted analytic torsion, where an analogue of the Cheeger-Muller theorem is proved, establishing the equality by using a new combinatorially defined twisted torsion. A catalyst for much activity in the area is his joint work formulating the magnetic gap labeling conjecture, which labels the spectral gaps of certain magnetic Schrödinger operators on Euclidean space. Evidence for the validity of the conjecture is given in 2D, 3D, and for principal solenoidal tori in all dimensions, which itself is a breakthrough. Congratulations, Mathai, and now to Mathai's presentation.
So one of my main areas of research is geometric analysis and index theory. So let D be a partial differential operator on a bounded manifold. That is, it contains derivatives. And suppose that it is elliptic, describing phenomena that do not change from moment to moment, such as a Laplace operator. Then one knows that the number of solutions to du equals 0 is finite, and so is the number of constraints imposed. The index of D is then the integer, which is the difference of these two numbers, namely the number of solutions to du equals 0 minus the number of constraints imposed. The index of D has various useful properties, namely it's invariant under deformations, it's invariant under compact perturbations. T and Singer, the winners of the Abel Prize in 2004, and who are pictured on the slide, gave a striking calculation of the index of D in terms of the geometry and topology that can be easily calculated by standard techniques in algebraic topology. So the ubiquitous applications of the Thier-Singer index theorem, it goes towards the classification of two-dimensional surfaces, towards the classification of four-dimensional manifolds, anomalies in quantum field theories, anomalies in string theory, quantization of conductance in the integer quantum Hall effect, in gauge theory, engineering, number theory, representation theory of Lie groups, obstructions to the existence of positive scalar curvature metrics, which is the same as positive mass, rigidity of scalar curvature. These are examples of a general principle. Suppose that one has a measurement in physics that is an integer valued multiple of a universal constant. Suppose also that it is stable under the addition of impurities and under deformation. Then it is more than likely to be expressed as the index of an elliptic operator. Then the Thier-Singer index theorem explains this measurement. For example, the quantum Hall conductance. In the year 2000, I was awarded a Clay Research Fellowship for a year and used it to work at MIT with Melrose and Singer. In joint work with Melrose and Singer, we introduced the concept of a projective partial differential operator, D, on a bounded manifold. It generalizes the notion of a differential operator. And suppose that it is elliptic, then it turns out to have an index which is now a fraction or a rational number. The index has various useful properties. It's invariant under deformations, invariant under compact perturbations. We gave a striking calculation of the index of D in terms of the geometry and topology in 2006. When D is an elliptic partial differential operator, then our theorem recovers or reduces to the Thier-Singer index theorem. And on the slide, you can see the picture of Richard Melrose, who visited the winery in Adelaide. Recently, a more general principle has emerged. There have been measurements in physics that are fractional valued multiples of a universal constant, and which is stable under the addition of impurities or under deformation. What plays the role of the analytic index in this situation? Well, it's more than likely to be expressed as the index of projective elliptic operator, which happens to have an index which is a fraction in general, then one can apply our fractional index theorem to explain this sort of measurement. An application is to the fractional quantum Hall effect, for which Sui, Stormer, and Laughlin received the Nobel Prize in 1998. The Hall conductance takes on fractional values. At temperatures close to absolute zero and low direct current J and very strong magnetic field which is perpendicular to the plate where the current flows, the Hall conductance, which is measured in the transverse direction, turns out to be fractional valued. This is the experiment of the quantum Hall effect in that picture. So use the methods of hyperbolic geometry and orbifolds as well as projective Hamiltonians in a model for the fractional quantum Hall effect. Of course, there are many other methods to show this. So I next come to an infinite dimensional version of my work with Melrose and Singer, but before that I'll give some background. So Edward Witten, pictured on the slide, computed the index of Dirac operators on the infinite dimensional manifold of small loops on a manifold. This index is no longer an integer, but is a series in powers of q. Under the assumption that the manifold has a string structure, the index is a modular form over the integers, which is a non-trivial result. It's been well studied by number theorists and is equivariant under the action of SL2Z, which is the modular group. So with my collaborator Fei Han, pictured on the slide, in 2019 I computed the index of projective Dirac operators on the infinite dimensional manifold of small loops on a manifold, generalizing the work with Melrose and Singer. This index is a series in powers of q with rational coefficients. Under the assumption that the manifold has a rational string structure, the index is a modular form over the rational numbers, which is again a non-trivial result that we prove. So the applications of these loop space index theorems include partial obstructions to positive Ricci curvature, rigidity of group actions on manifolds, identities in number theory, applications to string theory. Here the partition functions of string theory are modular forms that are often the loop space index. The modular property is closely related to S-duality in string theory. Some other related mathematics that I do research on is a fundamental duality in string theory is T-duality in a background flux H, where the T-dual spacetimes may be topologically distinct, but the string theories on these spacetimes are equivalent. A picture suppressing one dimension and illustrating this is the donut universe, which is pictured below, and with 1 unit of flux. And on the other side, it's a spherical universe with no units of flux. Thank you for your attention.
Now it's my pleasure to welcome live with us today Professor Mathai Varghese. Welcome.
Yes, thank you.
And warmest congratulations to you on being the recipient of the 2021 Hannan Medal.
Yes, I'd like to take this opportunity to thank the Academy for presenting me with this Hannan Medal. It's a great honor. And yeah, I also would like to thank the Australian Research Council as I hold a laureate fellowship, and this has helped fund my research. Thank you.
Oh, thank you very much for your incredible contribution. We always invite questions from the audience. Please pop them into the chat on the Q&A tab on your screen, and we'd love to relay those to our award recipient, Mathai Varghese. So I'll ask a very generic one, but how did you first fall in love with mathematics? Let's start from the beginning.
Well, way back when I was in school, I used to browse through my father's collection of books. He had a very interesting and large collection. And I found several that were inspiring and on mathematics and science, including a book by E.T. Bell, which many mathematicians would know about. It's called Men of Mathematics. Although it says Men of Mathematics, there were several women also featured in it. And it contained biographies of great mathematicians from the past, as well as a description of their famous research. And I would say that these mathematicians became my heroes. So that's how I started.
Were those women and men mathematicians from around the world?
Yes, they were around the world, mainly from Europe and US. Yeah, it's well, it all started there, let's say.
Yeah. You mentioned that your local library was a source of inspiration as well, and you'd borrow books in geometry, in topology, in other areas. I imagine you were quite young there. Were they really tough to understand, or was this a natural ability you had to read this sort of material and comprehend it and extract from it?
Well, I mean, I found mathematics easy in high school, and it was just not very challenging. But the math that I saw in these biographies and then later on in the books that I borrowed was far more challenging. But I thoroughly enjoyed the beautiful concepts and results once I took the effort to understand them. Of course, it was not smooth to do that, but eventually I did. And I always tried to solve problems which are posed in these books. So that made me good. It's not like reading a novel. You've got to actually solve the problem, etc. So
a fundamental skill of any scientist, problem solving, absolutely. In your presentation, you spoke about the time you spent at MIT.
Yes.
Have you been able to continue those collaborations, and how have they evolved over the years?
Right. Yes, this was the main formative period of my research. So in the year 2000, I was awarded this prestigious Clay Research Fellowship from Harvard, which I used it to spend a year at MIT to work with Isidore Singer and Richard Melrose. We had a great collaboration for an entire decade before Isidore Singer retired. And very sadly, he passed away earlier this year, but at the venerable age of 96. Yeah, he was a great mentor for me. Well, I have ongoing research projects with Melrose, and I enjoy those, and I continue to work with them even to this day.
It's extraordinary collaborations, and they are very deep and very personal. Thank you for sharing that with us. I think sometimes we underestimate just how critical figures such as mentors and collaborators are in science, and how much strength they bring us to continue our work. For those of us who are not in your field, can you give us a sense of how long you work on problems you're seeking to solve, and how do you approach the more complex ones, the more multifaceted ones? Is it years and decades of research? Is it broken down into small chunks? How does one go about such complex problem solving?
Yes, that's a good question. Especially in mathematics, it takes years to solve a good problem, and one needs long periods of concentration and uninterrupted thinking before you get the eureka moment. But to speed things up, I actually enjoy collaborating with others and bouncing ideas off them. And it's and the result comes a lot quicker, and it's a lot more fun, I think. I used to work initially just by myself, and yeah, it was so I enjoyed it after I went to MIT. So
It is similar to some of the words we've heard spoken from other awardees we've heard from today, and that some of that creativity and verification as well as new ideas comes from speaking with people and needing an enormous amount of trust to be able to, I guess, make yourself vulnerable with your knowledge or areas that you don't have knowledge in yet. So it's certainly worthwhile, but I imagine how challenging that in itself is if you've been used to working on your own. So thank you for sharing that with us. We have a question from the audience. Professor Malcolm Sambridge, Vice President of the Academy, asks, first he says congratulations, and then asks, how and when did you decide to focus on index theory as a major area of research? Do you recall the moment when you decided this was for you? Could you have gone in another direction or directions?
Yeah, so when I did my PhD, I was working, I did my PhD at MIT, and of course was influenced by Singer, but my supervisor was in a different area, and I kind of worked in that area. But in 2000, that was a game changer when I went to MIT. Singer gave some great advice. He said, don't work on things that only 5 people are interested in. You got to work on the main questions in mathematics. And of course, everyone thinks that, and at least people in Boston think that Boston is the Athens of mathematics, and you got to do Boston mathematics to be, really good and to be recognized. So he basically told me to forget my previous research and to do index theory and applications to string theory and so on. And it was around 2000. So I don't think, I think I was always fascinated by index theory. So to actually work with the legend himself, just improved my knowledge about it. And also I've, given this knowledge to my students and so on. So they, and the main thing is, the way in which he dealt with me. He was very kind and treated me like a son. That's it.
Sounds like a very wise choice and one that you've never looked back from.
Mm-hmm.
The next question for you is, your work is considered critical in understanding topological space. Is there a particular discovery or application that you're most proud of?
Well, that's a tricky one, but since I've been doing research for a large number of years, I have more than one favorite. So it started off with my work with my supervisor, and it became known as the Mathai equivalent formalism. It has applications to index theory and topological field theories, that is to some part of physics. And then to the mathematics of condensed matter. So again, it uses some index theory. To T-duality in a background flux in string theory. So it's a duality in string theory where I mentioned this in my slide, where the theories on topologically different spaces could be exactly equivalent. And then finally, fractional index theory and projective families index theory, which I mentioned in my slides. So these are the main things. I can't zero in on one because probably if you really ask me, maybe the last one, which is what I talked about mainly in my slides.
Fair enough too. It's many years of achievement, and you have every reason to be proud of all of it. Unless there are any other questions from the audience, I'll ask the last one. What keeps you going in your research?
So, for the past decade, I've been director of the Institute for Geometry and its Applications here at Adelaide. and providing leadership to the staff and students in pure mathematics is it gives me great joy. And so the Institute, I co-organize workshops, invite overseas experts in hot topics to give lecture series in Adelaide. And all these inspires staff and students there. As for my own research, I've outlined a very long-term plan in my laureate award. And this is definitely enough to inspire me to continue. While I also read about other mathematicians, I enjoy reading about their experiences. I also have a fascination for science, so like physics in general. Like I love the gravitational waves and LIGO experiments, and other experiments in physics. So I always keep up with that. So it's not just mathematics, but I also enjoy things in physics, even though I don't do, actual research.
Your colleagues and collaborators are very lucky to have you as part of their team. I'm afraid that's all we have time for. So thank you very much for your contribution, and congratulations once again on receiving the 2021 Hannan Medal. Thank you.
Thanks very much.
And now to introduce our next awardee, please welcome back Academy Vice President, Professor Malcolm Sambridge.
Thank you, Anna Maria. I am delighted to be here again today. This time, I join you to celebrate the 2021 David Craig Medal. As we heard earlier today, the David Craig Medal is a career award made in honour of the outstanding contribution to chemical research of the late Emeritus Professor David Craig. Its purpose is to recognise contributions of a high order to any branch of chemistry by active researchers. And this year, the medal was awarded to Professor Thomas Maschmeyer. Before we hear from Thomas, I will read his official citation. Thomas Maschmeyer's research vision is driven by a strong desire to help address the many urgent physical challenges we face due to climate change and global resource limitations, in combination with a growing world population. In this context, he sees catalysis as a key science and technology, and has made seminal contributions to catalytic research that have transformed how we design, interrogate under operating conditions, and use catalysis in petrochemical processing, as well as photo and electrocatalysis. His work has led to fundamental breakthroughs in catalytic materials, in situ characterization, green chemistry, hydrothermal processing, ionic fluids, and energy materials. He has translated many of his successes from his laboratory to scale, with his inventions adopted in various industry sectors globally to enable a circular economy, including petrochemical reprocessing of plastic waste, utilization of renewable chemicals, and energy storage through his emerging battery technology. Congratulations, Thomas. And now to Thomas's presentation.
It is a great honour to have been awarded the David Craig Medal and Lecture. My speciality is catalysis, making chemical reactions go faster. After a very rewarding early to mid-career, looking at mostly curiosity-driven research, I felt some of those insights could be fruitfully used and applied to problems that plague the planet. The twin issues of sustainability and resource scarcity have occupied my mind for a very long time. Turning waste into products that can re-enter the economy, thereby transforming it into a circular economy, taking care of the waste and extending the resources we have while reducing carbon dioxide emissions, all that together really excites me. Most of us will be aware of the latest release of the IPCC report, which calls us to ever more urgent action. I think chemistry has just got such an incredible toolkit with which to tackle these issues that chemists also carry an incredible responsibility to try and make a difference. My aim for today is to exemplify how research from the laboratory can end up on a successful path towards creating solutions at scale. First up, waste recycling. Reasonably pure waste streams have a chance of being recycled mechanically. Good examples are paper and cardboard recycling, or the recycling of PET bottles. However, these do not represent the majority of waste streams. Instead, complex and difficult, partially sorted mixed waste represent that majority. The key issues when looking to chemically upgrade such a mixed waste are the energy used in the process, the degree to which the waste needs to be pre-processed, the yield of liquid product, the stability of that product, the need for any post-processing. In mixed waste processing, these issues lead to nearly insurmountable barriers. Consequently, most of the biomass wastes are burned at their point of origin for process heat or put into landfill, whereas mixed plastics end up in landfills or incinerators, or in the environment. In Australia, landfill has been a key option for mixed end-of-life plastics. This is not the highest and best use. Neither is simply burning them. Instead, the materials should be reintroduced into the circular economy. Other than burying or burning, pyrolysis has been a technology people have been tried to deploy commercially for many decades. However, key issues are the instability of the product, the difficult and toxic waste slag generated, and the low liquid yields. As a chemical audience, you will appreciate that all of this is closely linked to the radical chemistry of that thermal conversion process. The plastic starts to decompose because the energy applied leads to thermal cracking of the polymer chains. The partial gasification and liquefaction of the waste introduces also some new cross-linking within the solids and the liquids, leading to extensive charring. Therefore, it is no surprise that pyrolysis of mixed waste is a low-yielding approach, generating a lot of intractable solids, similar to coke, but with all the inorganic polymer fillers baked in. But even the liquids generated are not stable and will cross-link into solids over short periods of time. Long-term storage for further conventional processing is not possible without expensive catalytic post-treatment with hydrogen. So now you know the problem. What can be the solution? With my startup Lyle, we developed the catalytic hydrothermal reactor technology. Principally, we are able to use water as the agent of change. It is involved in mass transfer, heat transfer, and also as reactant. Due to the special supercritical water reaction conditions and the manner in which we introduce the waste and the water into the reactor, it is possible to activate the hydrogen atoms in the water such that they transfer into the product. We believe that the radical chemistry involves water directly. Here you can see what happens when we run our process in deuterated water. The mass spectra show fragments of polyethylene that were generated in both normal water and D2O. Clearly, the D2O exposed fragments have shifted to molecular weights that are consistent with deuterium incorporation. Consequently, then, there should be less cross-linking, and indeed, on a carbon basis, we get around 15% gaseous yield, 82% liquid yield, and just a very small amount of solids that separate out with the inorganic fillers. The gas is used on site to run the process, so it runs itself essentially. This approach is now being rolled out globally with Dow, Mitsubishi, KBR and Shell, and is expected to process 1 million tonnes by 2025, plastic waste that would otherwise go into landfill, be burned or pollute the environment. Now to batteries. When examining the storage options that underpin the renewable energy revolution, a few things jumped out at me. Clearly, lithium-ion batteries, although extremely successful, have had issues around fires that are very difficult to control. Just a few weeks ago, Tesla's latest Australian very large battery installation caught fire after less than a day of use, and LG Chem had to recall 10,000 home storage unit systems from the US due to safety issues. So safety is a key concern for that technology. Toxicity and recyclability is another concern. Currently, only a few % of lithium-ion batteries are being recycled. In terms of state of charge limitations, as you can see here, both lead acid and lithium-ion batteries prefer incomplete charge-discharge cycles. In addition, to reduce capacity fade, air conditioning is often necessary. So what is needed is a battery that is close to fully recyclable, non-toxic, very safe, and can go anywhere between 100% and 0% state of charge, and do so at up to 50 degrees without the need for cooling. Zinc bromide battery chemistry offers such a solution. The battery chemistry is based on reversible zinc plating in combination with stabilized bromine. After some fundamental investigations around gels and their transport properties, I spun out Gelion from the University of Sydney to have a crack at commercializing a gel-based zinc bromide technology. This gel is able to control the chemistry of zinc bromide inside the battery in a manner that optimizes the movement of ions and electrons and manages issues around stratification as well as dendrite formation and gassing. The homogeneity of that gel, which then minimizes unfavorable concentration gradients inside the battery, is key to its success. Our design looks very much like a lead-acid battery. We are constructed in more or less the same manner and share many of the same materials. This means we can go into any lead-acid manufacturing site and retrofit the existing equipment at low cost. We can change these manufacturing lines into lines able to produce Gelion zinc bromide batteries. Remarkably, with this approach, it only costs about $16 million US to retrofit the machinery of an existing lead-acid factory to produce 1 gigawatt hour of our batteries. By comparison, if one goes to a greenfield site and builds a new lithium-ion factory, it costs around $125 million US. So our ability to use existing manufacturing capabilities is one of the reasons I believe that we have a chance to be commercially successful at scale. Battery technologies that have to introduce their own manufacturing capability from scratch face a much steeper uphill battle. Are we the only zinc bromide battery company? No. There's Redflow, an Australian company selling flow batteries. And there's a US-American company, EOS, like us, with a non-flow approach. However, unlike us, they are valued at $1 billion. Both those companies' designs feature bipolar electrodes and therefore need their own specialized factories, unlike our conventional parallel plate design. A design that is well received. We have interest for 400 megawatt hours of batteries on our books and are in partnership discussions with some of the biggest energy companies in the world. So I hope that with these two examples, I've been able to show that chemistry has the potential to make a positive difference to urgent problems. Chemistry is the enabling science, the science that can be relied on to come up with solutions for very difficult, often close to intractable problems. Being a chemist can be a very rewarding career path. There's a lot of excitement as well as a lot of fun to be had, let alone the satisfaction of applying chemistry for good. Thank you very much.
Thank you ever so much, Professor Maschmeyer. It is always so inspiring hearing you speak about your discoveries and research. Welcome and congratulations on receiving the David Craig Medal this year.
Thank you very much. It's a great honour to have received that medal.
We have an opportunity to receive questions from the audience. If you would like to ask Professor Maschmeyer any question, please fill in the Q&A section on your screen and I'll be able to ask those questions on your behalf. I'm going to start, perhaps from the beginning in a fundamental way. How did you first develop an interest in catalysis, finding ways of making chemical reactions go faster?
Yeah, so my history, I guess, goes back to being, I'm told age 2 or 3, mixing little bits of color on the windowsill in my parents' flat, and I was a great experimentalist, I'm told, and that really hasn't changed. Still keep doing that, and as I progressed in my understanding, I sort of, I guess, went to slightly more sophisticated things, and it's just exciting and amazing that there are catalysts which, in the biological systems, enzymes enzymes are super important to keep us all alive, and that selectivity by accelerating particular reactions in a whole universe of possible reactions. That selectivity and speed, to be able to do that rationally, that's just intellectually really exciting.
Absolutely. The solution you've come up for recycling plastic is absolutely remarkable, and I'm always so inspired to hear about it and learn more about it because, of course, plastics are a very, very big issue in our society. Also a solution for many things, but when we think about ocean plastics and things like that, goodness knows we need a solution at scale. And your discovery includes the use of water as a main ingredient. How clean is it overall? And are there any waste products at all from that methodology?
Right. So with waste upcycling, what you put in, you get out. So clearly, if it is full of toxic heavy metals, arsenic, that has to come out somewhere. But just assume it's the trash in the average trash can, then we'll have plastic that can be sorted in a mixed waste recycling facility into more or less industry accepted streams. And we can take those end-of-life mixed plastic streams, which will have been partially washed already a little bit, so bits of leftover burger and chicken will have been taken away. So those hetero elements from the proteins, the phosphorus, the nitrogen, which might give us some trouble in the oil later on, will have already been reduced. And we can take care of the rest through our process, where they report to the aqueous phase in our processing. So the materials we make are like-for-like replacements in chemical processing in the petrochemical industry. So we have naphtha, light cycle oil, industrial waxes, bitumen. So that is a like-for-like stream. And the dirty bits, if you will, go into the aqueous phase. But because our process is reducing to the oil but oxidizing to everything else, those materials are then end up as phosphates, as nitrates, etc. And they can be taken care of by just conventional water treatment.
It's remarkable. So even if it's mixed waste, all of those dirty bits, as you call them, they can all be separated out, regardless of what they are.
So that is our main calling card, I guess. Other people can't do it. So if I have a really high purity stream of polyethylene, I can do other things, and we don't need to go there. We can take the bits which are left over, and there's still a huge amount of that, and by far the majority. And we can do that. We can, as the only technology, do mixed end-of-life plastic at very high yields.
It's fantastic. So it is scalable. Obviously, one of the key challenges often in scientific research is making something scalable. How scalable is this technology? And could facilities like the one you've developed be built in a local government area across Australia, or perhaps not many are needed?
Right. So it is a matter of securing the supply. So we need about 20,000 tonnes a year to make the unit economically viable. But anything above that is fine. So we have one of the largest engineering companies in the world, KBR. They build oil platforms, satellites, all sorts of things. They run 60% and have built 60% of the world's ammonia plants. So they're really a big company. They've taken a worldwide license to roll this out in 120 countries, and they're designing units which are 20,000 tons, 50,000 tons, 150,000 tons, and 250,000 tons. So depending on the site, the appropriate size can be deployed. And much more than 250,000 does not tend to make sense, because waste is by its nature distributed. And at a certain moment in time, the transport of the waste is a net negative. So it's better to accumulate it in a more distributed fashion and then have smaller plants.
Yeah, I see. That makes sense. I was going to segue into battery technology, but we have a question from our audience that's doing just that. It's from Paul Mulvaney, who I'm sure you know. How does the zinc bromide battery technology compare with the Tesla wall? Could we see them as household energy storage? How does the end-of-life cost compare?
Right. Excellent questions, as always, from Paul. So we would do very well in a residential environment because of the safety. We are not as small as lithium ion, so that's our negative point, also somewhat heavier. But at the end of the day, it's the difference between, say, having a filing cabinet, which might be your Tesla or lithium ion battery, and and 2 or 2.5 filing cabinets, which are our battery. So if there's enough space of that sort of dimension, it doesn't really matter. The question might be, why aren't we going for the residential market straight up? And the reason for that is that I need to have a sales network with a lot of contacts for making really, really tiny sales. So what we are going for is larger sales, which might represent 10 or 100 household sales for a single one, and then build up from there. In terms of how clean it is, we've just got a third-party independent report on zinc bromide chemistry, and we are beating just about every other battery chemistry in terms of safety, in terms of toxicity, recyclability, use of water, and carbon intensity.
Absolutely fantastic. Thank you. Just moving on with battery technology, can you give us more of an appreciation of the research that went into the product that's now becoming available, and what were some of the stages and milestones in that development? It obviously didn't happen overnight. What were some of the key steps to get to where you are now?
Yeah, every overnight success tends to take at least 10 years. So I think, this is the Academy of Science. And so what's really important for the batteries thing, it was a failed project from an international exchange student where we tried to make a self-supporting ionic liquid membrane to separate pharmaceuticals, which had different functional groups. It was a complete disaster. I sent him away to relax a little bit before he wrote his final report and said, look, why don't we just put a blue dye and a red dye, mix it up, and see whether that membrane separates them. Just take 3 days to chill, come back and see what happens. And it sort of separated them. And the dyes had different charge characteristics. So I thought this could be useful for something, but it was completely useful for what we tried to do. 4 years later, I do a project for a company, Redflow, to help them with electrolyte, a zinc bromide flow battery, and these sort of two things merged in my mind. And after a while, I realized, well, that failed experiment actually could be used here, and that was the genesis of Gelion.
I love that story so much for two reasons. Of course, we know the pathway to success is full of failures, which aren't, of course, failures, but just that pathway and are needed. And also because of the wonderful discoveries that come from collaborations and interns and young scientists exploring. Absolutely phenomenal. It's very much the hallmark of what makes discovery. And I heard in that story as well, the young Professor Maschmeyer on his mum or dad's lap, mixing two things. Let's just throw in some red and blue. It struck me as a similar sort of process as you would have taken as a child. It's fantastic.
There's a continuum.
There is. Are there any challenges with accessing materials to make your zinc bromide batteries?
Yes, so zinc is mined all over the world, so that's an easy one. In Australia, there are a few mines. Well, there are a few mines for everything in Australia, so that's not new. And bromine or bromide currently is supplied largely from the Dead Sea via Israel Chemical Laboratories, who are our partner from the Israeli side, and then Albemarle from the Jordanian side. But then there's also big brine lakes in North America, and they are being used to take zinc bromide out to use actually as fracking fluid. So there's plenty of material about. So we don't have trouble with that. We also need carbons, but that is the same for every other battery. And of course, we need plastic casings and copper connectors and things like that, but nothing special.
I'm sure they are, but I see your point. So going to your own personal passion for chemistry, it's very, very easy to see by us at the Academy of Science, but I'm sure by the many audiences who have been inspired by your work. You describe chemistry as having the toolkit to overcome some of the world's biggest problems. Are there other problems in your sites that you'd like to tackle or that you're tackling now?
Yes, so I think a big one is ammonia. Ammonia is, of course, very strongly related. The Haber-Bosch process, very strongly related with being able to feed the world. And if you have a look at population growth on a global scale and the growth of ammonia production, it's basically one-to-one correlation. So that's great. And I'm not suggesting we stop that and have lots of people starve, but we generate about, well, depending how you calculate it, around 4 to 6% of the world's greenhouse gas emissions are associated with just that one process. So if I can make that process renewable, it's a huge global positive hit. And chemistry, I think, is the science which will need to do that. And so we are working on that a little bit, and lots of other people are working on this as well. And I wish them all the best so that one of us cracks this problem, which is very difficult.
All strength to you. Would you describe the international research effort in this area and in others more of a collaboration or a race? Is it the first to get this done? Or?
Nitrogen activation at lower temperatures is so difficult that I think it's still a collaboration. Once it starts to smell like big success, it becomes a bit more of a race. So there are lots of fundamental scientific questions still to be answered, and I think that's a really exciting area to go in for young scientists as well, because if you want to make your mark both in the intellectual breakthrough on the fundamental level and also then in the application, this is a dream reaction. People have been trying to do it for a long time, so Haber-Bosch is pretty good. But it, of course, uses natural gas as a source for its hydrogen, very high temperatures. It's very CO2 intensive as a process. So if we can electrify it effectively, that will be the way to go.
The Australian government's policy response to emission reduction is very much founded in technology being a solution. Do you feel that some of the technologies you're developing and others are that are underpinned by chemistry hold the key to the technologies needed for us to reduce our emissions, to meet our emissions targets, and to be able to do that at scale?
Yeah, I think markets respond to frameworks in which they have to operate. And I think by constructing frameworks to get certain kind of responses from the market will find that response. And those responses inevitably will use technology. But I think without a really solid, well thought through market framework, just relying on technology and say, the technology on its own will be so amazing that nothing else will matter, and it's just a logical, inevitable conclusion. We not necessarily will get the speed with which we need to act. So it's both. It's the technology, and chemistry is very much a part of that. Materials chemistry, process chemistry, energy-related chemistry. But also a good market framework, good policy framework is really key, because for it to go to scale, we need investment, and we need huge investment. Huge investment likes a degree of certainty and predictability, and that needs to be given by the government.
Thank you. I spoke with you when you won one of the Prime Minister's Prizes for Science, and I was inspired at the time, and I always remain very hopeful when I hear you present your research and the advances you're making. I know I'm not alone there. We often, certainly the staff at the Australian Academy of Science, speak about your work as an example of extraordinary achievement and one that gives many of us hope. So I'm going to ask you one last question, unless there are any others from the audience, and that is, what's your message to young researchers, and maybe not just researchers, but to young people in terms of the pace of research and technology to deal with some of these global challenges we are facing?
I think we have we've made amazing progress over the last 10, 20 years. If you think about solar technology, of course, Australian invention, Martin Green, UNSW, in terms of the current most efficient solar cells out there, and they've come down in price in the last 10 years by something like 95%. What a success story that is. And how has that changed the paradigm? Because we can really go for electrification of lots of things, which deals in turn with challenges in emissions. But think about vaccines. How quickly has the COVID vaccination come along? The promise in mRNA technology. What will happen to cancer? What will happen to heart disease? I think the world that will be the world we live in 10 years from now is going to be different, and I believe much better than it is right now. And, it's just such a privilege and so exciting to be part of that as a scientist, as a technologist, to be able to make a contribution. And I would really encourage any of the young scientists watching to follow their dreams, see what really, makes their heart beat faster, concentrate on that, and, don't be led astray, push forward and make your contribution, make your mark on the world for a better planet.
Absolutely. Thank you for that message. And thank you for all you're doing. The world will be a better place, and that's in no small part because of your contribution. So congratulations once again on winning the David Craig Medal this year. We don't have any more audience questions, so thank you for your time, Professor Maschmeyer.
Thank you very much. Great privilege. Thank you.
Thank you again to all our Science at the Shine Dome 2021 event partners. Our next Science at the Shine Dome event will be next Tuesday, the 14th of September, and then we will celebrate another 5 awardees. We hope you'll be able to join us then. My name is Anna Maria Arabia. Thank you for joining us, and good afternoon.